This is section 5.3 on the fundamental theorem of calculus. I'm doing part 1. There'll be a separate video for part 2. So here's the homework. 2, 3, 7, 41, odd, 59, 61, 63. So I'll show you all the homework, but I'm only going to do on this video fundamental theorem of calculus part 1, and then a separate video for so-called part 2. So this is page number 399, where the homework begins. Okay, so there's 2, and there's 3. We have 7 through 41. So 7 through 13 is there. That's fundamental theorem of calculus part 1. And 15 and 17. Starting with problem 19, it's fundamental theorem of calculus part 2, up until the last problems at the very end. So that's up to 27-ish. That's up to about 41. Okay. 59 through 63 is back to fundamental theorem of calculus part 1, which is what we're concerning with right now. Okay. So question 2, go back to that. Okay, so g of x is defined to be the integral from 0 to x of f of t dt. It's almost like an area function. 0 is fixed, okay, and as I move along to the right, I have a different net area or an integral, so to speak. So evaluate for 0, 1, 2, 3, 4, 5, and 6. I plug in 0, the integral from 0 to 0, well, that's 0. From 0 to 1, that looks like half a unit, so 0.5. If I go out to 2, that's a positive a half, that's a negative a half, so they cancel out, that'll be a 0. If I go out to 3, so this is cumulative, I've got negative a half, positive a half, negative a half, negative a half. So out to 3, I have negative 0.5. Out to 4, positive a half, negative a half, negative a half, positive a half, net total is 0. Then out to 5, where I already know from 0 to 4, that's 0. So here's another 1.5. From 5 to 6, there's 1, 2, and another half. So I add 2.5, that's 4. Estimate g of 7. Well, if I drew a straight line from here to here, that would be half of 3 halves. But since it's curving like that, I would think it's a little bit more. So I'm going to say it's 2 more units. So that's why I put 6. Okay, so we're talking about an estimation for the integral, which is a net area. All right, where does g have a maximum value and a minimum value? Well, the maximum is right here at 7.6, and the minimum is at 3, negative 0.5. And sketch the rough graph of g. So I go 0, 1, 2, 3, 4, 5, 6, 7, and y coordinates are 0, 0.5, 0, negative 0.5, 0, 1.5, 4, 6. Plot it, and that's that graph. Okay. Okay, 3a is somewhat similar. Okay, integral from 0 to x. So from 0 to 0, so I can show you both at the same time. From 0 to 0, you have 0. I have no more hands. Okay, from 0 to 1, looks like there's 2. Between 1 and 2, there's 3 more. 1, 2, and then if you look at the triangular region at the top, it's 1/2 base times height. That's another 1/2 of 1 times 2, or 1. So I add 3. Excuse me. Grand total of 5. Then between 2 and 3, the height is 1, 2, 3, 4. Okay. So I add another 2. That's 1, 2, 3, 4 divided by 2, which is 2. So between 2 and 3, I add another 2. So grand total of 7. Then between 4 and 5, it looks like I drop down half a unit. So I lose half a unit, 6.5. I drop another 1.5. So 5, 5. And then 6, 3, between 5 and 6, I drop another 2 units. And between 6 and 7, I drop another 1 unit. So it becomes 2. Remember, anything below the x-axis is counted as a negative. Okay, B, when is the function increasing? Well, it's increasing on the interval from 0 to 3. Right? If I were to plot it, you can see it's increasing there. Where do we have a maximum value? 3, 7. You can just tell from the chart the highest y value is at 7. And so I plot the graph. That's what it looks like. Okay. And now for fundamental theorem of calculus, part 1, FTC 1. Suppose we define g of x as sort of this area function, integral from a to x of f of t dt. So a is fixed, x moves. So if I move x around, I get a different area. Okay. I'm going to move a little bit to the right, call it h. So I have from x to x plus h. In between, I have a point x star. Where's x star? Anywhere between x and x plus h. It could be right in the middle, or it could be the left endpoint or right endpoint. It doesn't really matter. It can be anywhere you want. So x is less than or equal to x star, less than or equal to x plus h. All right, so g of x plus h minus g of x. G of x plus h is this region here. G of x is this one. So if I subtract, I have this region, which is almost a triangle, that red area. I'm going to say it's approximately f of x star times h. Okay? It's almost a rectangle. If f is continuous, okay, then the approximation of a rectangle is pretty good. Divide by h, g of x plus h minus g of x all over h is approximately f of x star. Take the limit as h approaches 0. If f is continuous, the limit of the left side looks like that. The right side limit as h approaches 0 of f of x star. So as h approaches 0, x star is forced to move closer and closer to x. So the right-hand side becomes f of x. The left side is a definition of g prime of x. Okay. So g prime of x is f of x. So that gives us the fundamental theorem of calculus part 1, abbreviation FTC1. Given a continuous function f, if g of x is defined to be the integral from a to x of f of t dt, key points is that this is a constant and this is a variable expression here, then g prime of x is equal to f of x. The derivative of this thing is f of x. In some sense, it's sort of like saying the derivative of the integral. But key idea is constant here, variable here. Okay, so that means number 7, g of x is the integral from 0 to x of radical t plus t cubed dt. G prime of x, all you got to do is replace the t's with x, square root of x plus x cubed. Don't actually integrate, don't actually differentiate, you just plug in. Okay, number 9, g of s is this thing, constant here, variable here. Final answer, just put an s there, s minus s squared to the 8th power. Okay, then we make it a little bit more complicated. Number 11, capital F of x is integral from x to 0 of radical 1 plus secant t dt. Okay, so the constant and variable need to be switched. If you switch it, then you just turn these two around. So the integral from a to b is the opposite of the integral from b to a. So I have negative the integral from 0 to x of radical 1 plus secant t dt. Okay, so if you ever have a situation where you have a constant and a variable, you're good. If it's variable to a constant, switch it around and put a negative. So now f prime of x is negative square root of, just put the x there, 1 plus secant x. Okay. So I'm going to rehash that idea for you. So on page 385, integral from b to a is the opposite as integral from a to b. Okay, And I'm using that property below that. I have no more hands, but the integral from A to A, how much area is there if I start at A and end at A? 0. There's no area there at all. Okay. And this addition property, figure 15, integral from A to C plus the integral from C to B is equal to the integral from A to B. Integral from A to C, that dark blue, plus integral from C to B, the grayish thing. Well, I got the same area as if I went straight from A to B in the first place. Okay. Okay, next complication. What if I have a variable expression, constant here, but it's not just x, it's e to the x. Okay. Then a chain rule is involved. Suppose I let u be e to the x. So h of x is the integral from 1 to u of ln t dt. Well, the chain rule Leibniz variation, h prime of x, I can say it's dh dx. It's dh du times du dx. Okay, so dh du, well, if I just follow the rule from before, I just put that right over there, ln u. And then du dx can be written as u prime of x. Change u back to what it was, e to the x times u prime of x. ln of e to the x is x times e to the x, or x e to the x. So that's the answer to this one, but now shortcut, it looks like if you have a function, put that function right over here, and then differentiate the function. So in other words, e to the x, put that right here, ln e to the x, and then times the derivative of e to the x, which is another e to the x. So I have ln e to the x times e to the x, or x e to the x. So here's another one like that. Y equals integral from 1 to 3x plus 2 of t over 1 plus t cubed dt. So you put the 3x plus 2 right there and right there for y prime. So t gets replaced by 3x plus 2, 1 plus 3x plus 2 cubed, and then times the derivative of 3x plus 2, which is just 3. Okay, 17. Variable, constant, switch it around and put a negative. Negative integral from pi over 4 to radical x, which is the same as x to the half. Okay, so for the derivative, just put the radical x right there, and then times the derivative of x to the half. So y prime is negative radical x, tan radical x, times the derivative of radical x, which is 1/2 x and negative a half. Clean it up. I have radical x, tan radical x over 2 radical x. Looks like radical x cancels out. So negative a half tangent radical x. Okay, then some problems at the end. What happens if you have variable expressions on the top and the bottom? That would be like 59 through 63. So 59, 61, 63, variable expression on the top and the bottom. So I see we have, for 59, 2x, 3x. So the way to do this is to break this up as the integral from 2x to, you can put any constant you want. Might as well just use 0. So integral from 2x to 0 plus the integral from 0 to 3x. That was our rule that we had before, where the integral from a to b plus the integral from b to c is equal to the integral from a to c. So 2x to 0, 0 to 3x gives me the integral from 2x to 3x. So I introduced a constant 0. Okay, and then I realized this is fine, constant variable. This one needs to be turned around. So negative integral from 0 to 2x and 0 to 3x. So now they're both good. So g prime of x is negative. Put 2x right there, 2x right there. So 2x quantity squared minus 1, 2x quantity squared plus 1, times the derivative of 2x, which is 2. Plus, same thing here, put 3x right there, 3x squared minus 1. Put 3x right there, 3x squared plus 1, times the derivative of 3x, which is 3. And just a little bit of cleanup. So negative 2, 4x squared minus 1 over 4x squared plus 1, plus 3 times 9x squared minus 1 over 9x squared plus 1. Okay, 6.3 is like that. cosine x, sine x. So I break it up into the integral from cosine x to 0 plus integral from 0 to sine x. This is constant variable. This is backwards, variable constant. So turn it around. Opposite of integral from 0 to cosine x, ln 1 plus 2 v dv. And now they're both good. Okay, so y prime is negative, temporarily negative, ln, put cosine x right there, 1 plus 2 cosine x times the derivative of cosine x, which is negative sine x. So these two negatives become positive. Plus, same thing here, put sine x right there, ln parentheses 1 plus 2 sine x times the derivative of sine x, which is cosine x. Okay, so just a little bit of touch up. Final answer, ln 1 plus 2 cosine x times sine x plus natural log 1 plus 2 sine x times cosine x. Okay, so that was FTC, Fundamental Theorem of Calculus, Part 1, and I'll have another video for Fundamental Theorem of Calculus, Part 2.